So there's this Italian guy named Cavalieri. He wanted to find the area beneath curves or functions. So this is Cavalieri over here. Bonaventura Cavalieri. According to him, lines and curves are all made up of tiny dots or points connected to each other. Because they're so small and can't be broken down any further, we'll call them indivisibles. Yeah, indivisibles. He was also the one who first described the area of inscribed and circumscribed rectangles to be approaching a limiting sum. Say you have a curve over here. To obtain the area, that would be equal to adding the individual areas of these rectangle shaded regions beneath the curve. So if you get this rectangle, add the area, and so on and so forth with the next rectangles, you should eventually approach a sum, and that sum is the area of the curve. To prove his theory regarding indivisibles, he utilized the theory behind the area of a triangle, which is base times height over 2. He's trying to prove that adding the indivisibles will let us effectively compute for the area of a region. So we know that the area of a triangle, or the region under the curve for this example, is 15. By definition, the ratio of the area of the triangle to the area of the rectangle is 1/2. Remember that. So if we use his method and plug in the values for the individual area of the rectangles, we see that the ratio of the areas of the sum of the indivisibles and the individual rectangle is 15 over 30. Whoa, it's 1/2. When we plug in bigger values, like say a rectangle with sides 10 and 11, the ratio apparently still holds, so here we have 55 over 110. Oh, it's true. It's still 1/2. So to formalize, the following equation can prove that the concept of indivisibles can effectively get the area under a curve using a triangle in particular for this example.
Now, onto parabolas. So we draw the graph y equals x squared with an n number of rectangles and draw a bigger rectangle containing the graph at 0 to n. Let's say n equals 3, and we draw 3 rectangles with the same base. The base of the bigger rectangle is n plus 1, while the height is n squared. The theory relies on the base of the triangles always being 1. The height is signified by the graph x squared. We then get the ratio as follows: area of the shaded rectangles over area of the bigger rectangle, which will eventually become 14 over 36. The 14 over 36 can be broken down into 1/3 plus 1 over 18. Generalizing, we get 1/3 plus 1 over 6n. We get the limit of this as n approaches infinity in order to get the area under the curve. As n approaches infinity, 1 over 6n becomes negligible, so the ratio eventually just becomes 1/3. Meaning 1/3 of base times height would be equal to the area of the shaded region, which is the foundation of the integral 1/3 x cubed. Now let's prove graphically why increasing the number of rectangles, whether inscribed or circumscribed, will eventually lead to the area of the curve. So So I'm gonna illustrate the graph y equals x squared with bounds a and b. N will also be the number of rectangles. In this first case, I'll be starting the rectangles from the lower bound, or the left side of the graph. This is called the left Riemann sum for obvious reasons. Because of the positive slope of the function, all the rectangles end up under the graph, which makes it an underestimation of the actual area. On the other hand, when I start drawing the rectangles from the right side or the upper bound, this will be called the right Riemann sum. Again, due to the positive slope of the function, they will actually end up over the graph, which makes it an overestimation of the area. Let's first show the proof using the left Riemann sum. As you can see, as we increase the number of rectangles, the underestimation becomes lower. As we increase it further and further, the underestimation becomes very small to the point that it is negligible. This also applies to the right Riemann sum as well. The overestimation decreases. Thus, we obtain the real area of the curve.